So welcome back from your break. Hope you had loads of fun, and none of you got sick in the meanwhile, and everybody's healthy. So to continue what we were doing last time, so let me give a quick recap of what we did up until the point before the break. And if you have questions or things about what we did, need clarifications, now is a good time to ask. But in general, we started the course with a discussion of a magnetic moment, a classical magnetic moment, interacting with a classical field, or the classical magnetic field. Then we moved on in our discussion to talk about a quantum spin. Interacting with a classical field. We talked about nuclear magnetic moments, and we even built an NMR quantum computer model, and we understood how that works. And then later, after that, so this was our quantum spin with a classical field. Then we talked about a quantum electromagnetic field. So there was no two-level system, no atoms there. And what we learned from there, if you remember, is that the electromagnetic fields is just a bunch of oscillators, harmonic oscillators. And we even built a small model for a quantum computer modeled on a single qubit, single photon qubit. So, and what we're going to do, what we're going to move on now to, we're going to basically be talking about a quantum spin, specifically a spin half. And we're going to have a quantum electromagnetic field. So if we go back to what we did before, then when we looked at the dynamics of an atom, or so an atom, or more specifically a two-level system, spin half, whatever you want to call it, then we had some, this just symbolizes the potential, and we had some two-level system, which we called 0 and 1, that also symbolized our qubit, or sometimes we call them ground and excited, so G and E, doesn't matter. And when we looked at the dynamics, we saw that if you drive it, so we had some energy difference here, h bar omega q, omega qubit, and when we drive this thing with a classical field, what did we get? Anyone? So if we look at the probability to be in the excited state as function of time, what do we get?
Rabi oscillations.
Rabi oscillations, exactly. Okay, and we got Rabi oscillations. These were those dynamics. And when we looked at the electromagnetic field, what we saw is that if we look at a single mode in the electromagnetic field, so a single frequency, we get a harmonic oscillator, a quantized harmonic oscillator with discrete energy levels, so 0, 1, 2, so this is the Fock basis, so 0 photons, 1 photon, 2 photon, 3 photons, and so on, where the energy difference between these is h bar omega. I wrote here omega c, but also h bar omega c, and so on, so all equidistant. And we even wrote specifically the operator, the electromagnetic field operator. If you remember, we saw that it is E_I epsilon star A minus epsilon A dagger. And we also discussed the state which is closest to a classical state. Anybody remembers what it was?
Coherent state.
A coherent state, exactly, which we symbolized by some number alpha. This is the state alpha, where the magnitude of alpha with resemblance to a classical oscillator was the amplitude of the oscillation, and the argument of alpha, the angle, this was the phase of the oscillation, where, and alpha squared, that was n bar, the average number of photons in that field, and we saw that the field is Poisson distributed around this n bar in this oscillator. And that kind of recapped our discussion, and also single photon state we talked a little bit about, and so on. And so what we're going to do now, and what we're going to move on to, is basically adding an interaction between these two things now. So this is what 4 is going to do. And we're going to talk about a model. What I want us to get to today is we're going to be talking about what is called the Jaynes-Cummings model, which is an approximation of the system. It is a very useful model for many, many systems. So just to start constructing it, I want you to first think about a cavity. Because this model discusses the interaction of a single electromagnetic mode, so a single quantized harmonic oscillator, interacting with a single two-level system. Okay? And in free space, we don't have a single electromagnetic mode. We have many electromagnetic modes. So to get a single electromagnetic mode, what I want you to think about is some cavity. Sorry. So we have some cavity, so we have two mirrors over here. If I'm going a little too fast, stop me or slow me down. We have two mirrors, and the boundary conditions gives us electromagnetic mode, so this would be the first mode, this would be the second mode, and so on and so on, if we're thinking of this as a one-dimensional cavity. But imagine that these modes are separated enough in frequency. So we're working, let's say, close to this fundamental mode. So this is the cavity. So inside this cavity is our harmonic oscillator. So A and A dagger are the operators that describe the field inside this cavity. And to get power and field into this cavity has to be coupled a little bit to the outside. So let's say one side of the cavity is just slightly transparent. Let's see, 1% or 0.1% or whatever number you want. It is coupled to the outside with some rate kappa. What this means in practice, and we're not discussing open quantum systems, and to do this properly we have to discuss open quantum systems, so I'm just going to tell you and give you results. But what this kappa means, it means that if you put in a coherent state into this cavity, the amplitude, okay, the coherent state will decay with an exponential on the time scale of kappa. Okay, so the light in here is leaking out at a rate kappa. Also, to create a coherent state and to drive this cavity, you can put in power in through the side. Okay, so you can drive this harmonic oscillator with the drive, but it also has a damping term, kappa. And the way you describe this, so the Hamiltonian for this cavity, for the single mode system, is just going to be h bar omega cavity, where omega refers to this mode that we're going to be looking at, A dagger A. This is our harmonic oscillator, plus the drive term. Okay, where the drive term is just a field, so it's going to be our epsilon A dagger e to the minus I omega pt, where omega p is the frequency of this pump over here. It may or may not be omega c, but in general there's some frequency omega pump, plus of course epsilon star A e to the I omega p t. So this is the drive term for the cavity, and this is A, where this epsilon here is the amplitude of the field that we're putting in. It's the amplitude of the sine drive that we're driving here, but there is some interplay because there is a sine drive coming in and there's also something leaking out. There's going to be a little bit of interference, and like I said, you need to study the system to get the result, but I'm just going to give you the result. And let's suppose that this mirror here is completely opaque and everything that comes in here comes out here, and it's completely one-dimensional. Then the power going into this cavity has to equal the power going out of the cavity. And this power is just h bar omega kappa over 4 times n bar. I didn't derive this, but let me just qualitatively give you what's going on here. H bar omega is the quanta of energy in the cavity. Kappa is the rate at which photons leak out. So if I just had some cavity, say I wasn't pumping it at all, but somebody put in some coherent state with n bar, then it would leak out at a rate kappa. So the power that I would see coming out of the cavity is just going to be some h bar omega kappa times n bar. This factor of 4 comes from the fact that I'm driving and there's reflection, so the interference causes this factor of 4 over here. Now n bar is just going to be related to epsilon, so I'm going to replace n bar with what epsilon is. So we're going to have h bar omega kappa over 4 times 4 epsilon squared divided by kappa squared, which gives us h bar omega epsilon squared over kappa. And the whole purpose of this is simply to show you that it doesn't matter what kappa really is here too much. I can always set whatever power I want to induce whatever coherent state I want, and that will generate some epsilon. And P is related to epsilon through square. Okay? That's it. This is what I wanted to show you in this part. And now what we're going to do, that we have this harmonic oscillator system, what are we going to add to it? What do we want to add? Anyone?
Atom.
The atom. Okay, so we're going to put our little dipole over here. I don't know, mark it with an X or whatever you want. Maybe a line. It's an antenna. It's a little dipole. And what we're interested in is the model that describes the interaction between this field and dipole. Okay, so we're going to be looking at a quantum spin half coupled to a single quantum harmonic oscillator. And the model that we were going to derive, so we're going to start off with a model that's called the Rabi model. This is the model that describes this. And then we're going to take something that is called the rotating wave approximation. And we're going to arrive at what is called the Jaynes. How do you spell Jaynes Cummings? With one N. Jaynes Cummings model. So this is our plan. And now this model is very famous, and it's ubiquitous because it comes around in many, many systems which are relevant to quantum technologies. So you will see it in many systems. You will see it in cavity QED. To remind you, cavity QED is literally the field where you have two mirrors. It basically looks like this. You have two mirrors around terahertz frequencies. You can drive these mirrors just like that. And the atoms are not stationary inside. You don't trap them inside, but you just send them through and they go flying through the cavity. So there's some interaction time where the atom flies through. Two levels, which are effective dipole, are interacting with the electromagnetic field, and then the atoms flies out. So that's cavity QED. So this is atom flying through cavity. The second field are trapped ions. In trapped ions, again, you have these ions and two levels. From this ion, two levels of ion interact with the motional degrees of freedom. Motional degrees of freedom. So here we have an electromagnetic field, but you can also quantize vibrations. And in trapped ions, the harmonic oscillator is not a quantized electromagnetic field, it's quantized vibrations of the ion. So the ion is trapped in this trap, and you're going to have a guest lecture by Roy Ozeri on the January 17th. There's already a link to that Zoom lecture on the website. So on January 17th, you're going to have a guest lecture where you will learn about the system, how it works. But the two-level system there interacts with the harmonic oscillator in the same way, only the harmonic oscillator describes the motional degrees of freedom of the ion. And you can have a chain of ions and they can all basically interact with the motional modes of these ions. But this model that we'll discuss is still going to hold there. Another system is circuit QED. This is what I do. This is also called superconducting qubits or superconducting circuits. And what you have there are artificial atoms coupled to microwave cavities. And these artificial atoms, these are basically circuits made out of superconductors. Okay? And these circuits, they're about millimeter size, but they behave as effective atoms. And these effective atoms are coupled to microwave cavities. And in that case, the microwave cavity can sometimes be a physical cavity, or it can also be another circuit itself, which behaves just like a harmonic oscillator. So also, the Jaynes-Cummings model that we're going to discuss is going to be good for this system. And last one, also you're going to have a guest lecture on January 24th. That's the last lesson. Neutral atoms. So Yoav Sagi, he does cold atoms. He's going to tell you how you can trap these neutral atoms. You can catch them with these optical tweezers, and how that forms a platform for quantum computation. And you will see the Jaynes-Cummings model also show up in that. So if you look at all these fields, which are the leading fields and the leading technologies for quantum computation, they all lie on this basis of this model. And also many, many papers that you will open up assume that you know this model. Okay? Now, there's this more generalized model, which is the Rabi model, which we will write in just a moment. But papers usually will start with this model, the more simplified model, and I will explain that in just a second once we understand this approximation. Okay, so let me write down the Rabi model, which explains this general situation, and then I'll explain what we're going to do with this rotating wave approximation. Okay, are there any questions so far about what we're going to do, how we're going to do it, why is it important? Anything like that? No. Okay. Oh, these pens are terrible. Try this pen. Okay, so this is the Rabi model, and this is the model you would construct if you just sat down to think about the system. Here, this is our system. We have our harmonic oscillator, and here we have our little dipole. So what this model assumes is, one, it assumes that our atom is a dipole. It has a dipole moment that couples to this field. It has to be much, much smaller than the wavelength of the field, such that the atom sees a uniform field where it's sitting. So think about a point-like dipole. So that is one assumption. And also we're assuming that there are no higher order terms that are coupling, like a quadrupole or so on, coupling to the field. So it's really the simplest model you can have for this two-level system. Well, two-level system may not have higher order terms, but maybe a more complicated will have higher order terms. So it's the simplest model for this two-level system coupled to a field. And our Hamiltonian in general is just going to be the Hamiltonian HQ. This is the Hamiltonian for the atom, for the qubit, the two-level system, plus the Hamiltonian for the cavity, which we're going to take single mode there, plus the interaction term, where we're assuming here in the interaction, we're assuming the dipole approximation, which means basically that A naught is going to be much smaller than lambda, which is the wavelength of the electromagnetic mode. Okay, that's an underlying assumption. Now HQ is just what you're familiar with, omega q over 2 sigma z. HC, this is going to be h bar omega c A dagger A. This is our harmonic oscillator. The interaction term basically comes from minus d dot E. This is what we saw when we talked about a quantum spin coupled to a classical field, but now we're going to replace E with our operator for our quantized field. So it's going to look like this, minus d epsilon q. This is the polarization of our atom, sigma minus plus epsilon q star sigma plus dot I epsilon naught. Epsilon, see, this is the polarization of the field. Although if you're thinking of a cavity really, and you're thinking of a one-dimensional model, well, we're going to drop that soon. Okay. So all we did now is we basically put here our quantum field. So this is our interaction, and this is called the Rabi model. Now, it has a very general solution. This solution was found a few years ago. It is a very complicated and usually non-instructive. It's not an instructive model to work with, and this is why people research all kinds of corners of this model. So you go to certain regimes to see certain phenomena, because the general solution is not very instructive in the physics sense. But what we're going to look at right now is what is called the rotating wave approximation. So we're going to do that thing, or we're going to do a partial derivation of that, which will get us to the Jaynes-Cummings model, and then we're going to look at what happens there. So we're going to look in that phase corner of phase space of the Rabi model, and it works very well for many of the systems. Basically, to get into regimes where the Jaynes-Cummings model doesn't work well is very hard experimentally. So the Jaynes-Cummings model is actually a very good model for all these systems, all these experimental systems. And when we derive, and I'll show you the conditions for this, I'll mention why that is. Okay, but first, let's focus on this, on the rotating wave approximation, and see how how we're going to reduce this model. Are there any questions till now? Is everything clear? Am I going a little too fast? No? Okay. Okay, so to discuss the rotating wave approximation, I want to do a quick reminder of three things, so then you can follow the approximation very quickly. Okay, so we're going to talk about three things. Rotating frames, transformations, and the interaction picture. Now you've seen all these things before. I'm just going to give a quick reminder on the board, because once I write a quick reminder of these things on the board, then the steps of the rotating wave approximation are going to be much simpler. Okay? So 3 things I'm going to do right now on this board. So the first thing is a reminder, and I think I did this also at the beginning of the semester, is a general transformation. So when you do a general transformation, if you write the Schrodinger equation, for example, so this is rho, the density matrix. We know that it's minus I H rho. In the new frame, rho transforms like U rho dagger. And in the new frame, the equation rho tilde dot is just minus I H tilde, the Hamiltonian, in the new frame, rho in the new frame. Where this is rho in the new frame, but H in the new frame is transformed like this. It is U, H, U dagger, minus I, U dot, U dagger. Sorry, there's a plus, not a minus. There's this time-dependent term. Sorry, there's this term that comes about when you when U has a time dependence. The second thing I want to remind you is what is called the interaction picture. The interaction picture is when we take a transformation and basically we're trying to find a term to cancel out this term. This is the way I think of it. Okay, so you have some Hamiltonian which you break up into H naught, which is time independent, plus V, which is time dependent. So this is going to be time independent. So this is time independent. And then what we do is we choose our transformation U to be e to the I H naught t. And then when we apply this transformation to our Hamiltonian, then H tilde, so H in our new frame just becomes U V U dagger. And this basically comes about because if you calculate U H naught U dagger, that just becomes minus I U dot U dagger. So these two terms, this one and this one, simply going to cancel out. third thing, which is very related to this interaction picture, is going into rotating frames. So suppose that, so 3 rotating frame. So suppose that we want to go into some rotating frame, and this frame is rotating at some frequency omega p, and I chose omega p to relate us to the pump frequency that we're pumping the harmonic oscillator. Remember, with the harmonic oscillator in the model, we had some frequency omega p, and we were pumping our cavity. We were injecting energy into the cavity with a laser. For example, laser working at omega p. And so in that case, we'll choose some unitary that rotates at omega p. So we'll have e to the I omega p, a dagger a, t. Okay, so the frequency you want to go into and the operator that you want. Okay, a dagger a, this is the number operator for a cavity. T. And so if you apply this unitary to our Hamiltonian, if you remember our Hamiltonian plus drive, we had our harmonic oscillator with a drive term. Maybe I'll write it down. So the harmonic oscillator with the drive term was h bar omega c a dagger a plus, do I have it here? Okay, never mind. Plus epsilon a dagger e to the I omega pump t plus epsilon star a e to the minus I omega pump t. So this is our Hamiltonian, and now we transform it according to U. Now to transform it, we're going to be using the Baker-Campbell-Hausdorff formula. Yeah. Like I promised you, it will show up again and again and again throughout your physics life, and throughout this course also. So here it is again. And if you use it, you will see that if you have some e to the I alpha, a dagger a, alpha here is omega p. So maybe I'll change this to omega p. Okay, so let's just put omega p a. This is going to be omega pt, but it doesn't matter. Here, just leave it general. Sorry, I'm not confused. I'll leave it general. And then e to the minus I alpha a dagger a. And if you use the BCH formula to do the commutation relations, you will find that you end up with e to the minus I alpha a. If you do the same thing e to the I alpha a dagger a on a dagger e to the minus I alpha a dagger a, you basically get the same thing, only without the minus. So a, because it doesn't have a dagger, it gets a minus, whereas a dagger gets a plus because dagger looks like a plus. So for our driven oscillator, if we do the transformation on this thing, what we will get is H tilde equals omega C minus omega P A dagger A plus epsilon A dagger plus epsilon star A. Now the Hamiltonian over here, this is, all I did is take this transformation and did this general transformation on this Hamiltonian. So this is the general transformation applied onto this Hamiltonian. If I now went into the interaction picture, I would take this, I could take this part and go, let's say, omega P equaled omega C. Or you can go into a picture where this goes away and this gets time dependences with exponentials, only the exponentials will have the difference of omega C, omega P. So you can choose what frame you want to look at. Right? But what we did here is basically go into a frame that is rotating at the pump frequency. Okay, so this is very general, going into a frame that is rotating at some frequency. If you go into a frame rotating at the frequency of the cavity, then you're getting this change of frequency. This would go to 0 and you just have the drive at the cavity frequency. Okay, so if omega C equaled omega P, if we were pumping right on resonance, you just see this term, and you can see that this term just gives you a coherent state over time. So a growing and growing and growing coherent state. So this is what the transformation going to the frame rotating at a pump looks like for a harmonic oscillator. And if we're driving on resonance, we would just get, again, this term. This term would cancel out. Now I want to do the same thing. Maybe I'll do it here, this little square. The same thing or a similar thing would happen if we go into the frame that is rotating with the frequency of our spin. Okay, so we have omega C. This is the frequency of our cavity. We can also see what happens if we go, let's say, into a frame that is rotating at the frequency of our spin. So think about the Hamiltonian for the spin, and you can choose u e to the I. Again, omega p, that's some frequency that you want to rotate at. That's why I'm keeping it omega p. But now I'm just going to have sigma z over 2 times t. So instead of a dagger a, this is sigma z over 2. And if you remember, in the Rabi Hamiltonian, we had sigma plus and sigma minus. So I want to calculate the commutations with those. So if you do u sigma minus plus u dagger, you will get, in the same way, e to the minus or plus I alpha sigma minus plus. And alpha is whatever is written here. Okay, again, it's a general thing. So alpha is just omega p over 2 in our case. And so with this understanding, what we're going to do now is we're going to be very brave, and we're going to go into a doubly rotating frame. We're going to go into a frame that is rotating at the cavity frequency and at the qubit frequency. Okay, so we're going to construct a U that goes into both frames. And you will notice that it is exactly the U that you would choose if you wanted to go into the interaction picture. Basically, if we go back to this Hamiltonian over here, I'll wait till the camera, there we go. If you go back to this Hamiltonian over here, you can see that you have these two parts which are H naught. And it's basically like going into the rotating frame rotating at this frequency and this frequency. Okay, so we're going to choose U to go into this doubly rotating frame, or you can call it interaction picture. And then we're going to do this transformation, and we're going to see what the Rabi model looks like in that picture, and then it will be easier to discuss what is the rotating wave approximation in that picture. Okay, so this is what we're going to do now. Is everyone following till now? Okay, I can see several nods. Okay, good. Okay, so now we go into, I don't know if you can say doubly, but you know, doubly rotating frame. So U is now going to be e to the I omega cavity A dagger A plus omega Q over 2 sigma Z T. Now I know that it's two frequencies, and each frequency has a different operator, so it makes your head spin. No pun intended, but yeah. So it's a little difficult maybe to imagine what this is, but this is the transformation, so it's well defined in that sense. And then H after our transformation is going to be the following thing. So this is H. So we have omega naught, and omega naught is the vacuum Rabi frequency that we defined previously. I'm going to write it down in just a moment, but for now it's just a constant. And then we have A sigma plus e to the I omega Q minus omega C T plus a dagger sigma minus e to the minus I omega Q minus omega C T plus two more terms, also omega naught, A sigma minus e to the I omega Q plus omega C T plus a dagger sigma plus e to the minus I omega Q plus omega C T. I think I have a mistake. Hang on, let me fix it. This should be minuses, and this should be plus. There, fixed. So this is what we get after the transformation. So this is still the Rabi model. This is just the Rabi model. In the interaction picture. And if you look at the four terms over here, they basically come about, if we move to this board over here, can the camera move? Thank you. They come about from these terms. So you have your sigma minus and A over here, and you have your sigma plus and A dagger, and sigma minus A dagger, and sigma plus A. So those are the four terms for the operators, and all the work that we did is just to show you the frequency dependence, basically how they oscillate in time in this interaction picture. So let's go back to this board over here and look at these four terms. So if we look at these four terms now, sorry, you can see that I've grouped them into two groups. One group is slow rotating. They're rotating at a frequency which is omega q minus omega c. And fast rotating, omega q plus omega c. Now at this point, many books, most books, will tell you, okay, omega q is going to be relatively close to omega c. So this is much bigger than this. And hocus pocus, this is fast rotating, so it averages out, and thus we can neglect this. That is the usual explanation. It is not wrong. It is actually true. But I find it kind of unsatisfying. Okay, now we're not going to do a rigorous derivation, but I'm going to give you the concepts of the more rigorous derivation and send you to the right literature. Okay? So, rotating wave approximation. And after I discuss the rotating wave approximation, I'll get to the Jaynes-Cummings model. I'll write it down, and then we'll take a 10-minute break because I see that I'm over time. Okay, already with our break. But so the rotating wave approximation, typically what is stated in books, in many books, is, okay, omega q minus omega c is much smaller than omega q plus omega c. Thus, these terms are going to be spinning very, very fast and can be neglected. So this is usual claim. I would say that a lot of books also add the second thing, which is sometimes more forgotten, and this is the fact that omega naught, so this is not sufficient really. To make the rotating wave approximation work, you really need omega naught to be much smaller than omega q and omega c. And the way you can understand this is because this rotating wave approximation is really about perturbation theory. Now doing this rigorously is quite a headache. But if you do this, and you can look in several sources. I'll give you the sources, and then I'll explain in general what they show. But one good source, very rigorous, but maybe a little hard to read, is Cohen-Tanuji's book. Atoms and Photons. It's called Atoms and Photons Basic Processes or something like that. I don't remember. He has two very good books. One is Atom-Photon Interactions, not that one. The other one is this one. That's basically as rigorous as you can get it. You will find it there. But a very nice derivation that doesn't discuss an atom with a field, but two harmonic oscillators, but basically the same thing is done there for two harmonic oscillators, is if you open the following paper, so on archive. Does everyone know what archive is? Do like a little X if you don't know what archive is. Are there any X's? Okay, all right. So some people don't know what archive is. So go into www. All good scientific papers, before they get published in real journals, the authors will put it up. It's an open server where you upload your drafts before you send to publication. Archive.org. And many of the published papers, you can find their preprint version on that website. And each paper just has a number. So you want to look for 1601-075-28. This is actually good. If you learn anything from this course, it's that there's archive and you can go look for scientific papers there. Okay? That's the most important thing, baby, in this class. Okay? Go to this paper. Don't read the whole paper. Go to Appendix A. Okay? Just go to Appendix A. You will see the derivation for those two harmonic oscillators and a relatively rigorous, a very rigorous discussion of the rotating wave approximation showing the terms of the perturbation theory. And then you will see the terms go like omega naught over omega q plus omega c and omega naught over omega q minus omega c. And then it is much clearer why we can throw away these terms. And also it becomes there much more clear that the more stringent requirement on the rotating wave approximation is that omega naught is smaller than these two, rather than this. Because omega naught can be relatively far away from omega c. So omega q minus omega c can be slightly smaller, but on the order of omega q and omega c themselves. And the rotating wave approximation will still hold, given that omega naught will be sufficiently small. Okay? So I would say the more stringent requirement is this one. But you've got to be careful when you're looking at the Rabi model and moving to the Jaynes-Cummings model and throwing this away. But in real systems, it is typically very safe to do that transformation. Okay. So once we throw away these two terms, then we can write our Jaynes-Cummings Hamiltonian. So maybe I'll move back to this board. So now I can write the Jaynes-Cummings Hamiltonian. And if we throw away these two terms, then we get that our interaction term is now some minus I h bar omega naught over 2 A sigma plus minus A dagger sigma minus. Where the Rabi frequency, just so I don't leave you hanging, is 2 over h bar d epsilon naught epsilon q star dot epsilon c. Okay, so we're left basically with this term over here. And you can see that what this term does is it exchanges quantas between the harmonic oscillator and our two-level system. If we go back to over here, it is this term over here. You can see. Only we went to a frame where we got rid of these time dependencies. So let's just focus on these terms over here. Also, in many books, you will see the argument for the rotating wave approximation given as an energy conservation argument, which is not wrong, but you got to be careful with it. But if you look at these two terms, what do these two terms do? Suppose that I have a photon in my cavity. What happens? That photon gets destroyed and an excitation gets created in the spin. And then what happens? The excitation gets destroyed in the spin and created in the harmonic oscillator. So there's an exchange of quanta between our atom and our field. A coherent exchange at a frequency of omega naught. We're going to go into the details of that in the next hour. These two terms, what happens is you're destroying two excitations, or alternatively, you're creating two excitations. So if you take the claim that omega q and omega c are close to each other in frequency, these two terms are more energy conserving, where these two terms are not, because you're destroying. You're destroying two excitations, or you're creating two excitations. And with no external drive, where are you going to get this energy? Okay, so you can apply an energy conservation term to why these two things cancel. Okay, so the fast rotation and the energy conservation, they're all physical insight into the more rigorous claim of the math behind the perturbation theory. And they're a good point to remember when you're thinking about these approximations. Okay, so what we should do now is take a 10-minute break, think about what we saw now, and then what we're going to do is we're going to study this Jaynes-Cummings model. So we're going to look at the model, the Hamiltonian that I wrote over there, and we're going to see what it looks like in two regimes. One, the resonant regime, and two, the dispersive regime. Okay, so we're going to look at those two regimes. Okay, so take a 10-minute break and we'll continue.